Hi, I'm Fernando Pereira from UFMG, and today we shall talk about another optimization that's common on JIT compilers, value specialization. There are many ways to perform value specialization, that is, to generate code assuming that values are constants. We will see how to perform this kind of a specialization on the parameters of functions. Why on the parameters of functions? Because most functions tend to be called only once or always with the same arguments. This is a study published in 2013. So if we look into the number of times that each JavaScript function is invoked in different websites, we meet a power curve. Most of the functions are called only once or twice, and there are really very few functions that are called more than, say, 20 times. And if we look into the values of the arguments of these functions, then the difference is even higher. About 60% of all the functions are called always with the same values in the arguments. That includes, of course, the functions that are called only once. That's true for JavaScript programs in actual web pages, but it's also true for benchmarks. Here we see three different benchmark suites. So, provided that this observation is true, we can apply the following idea. Assume that the argument of a function is constant when generating code for that function, and if the function is called again with different values, we can either trash the binary that we have produced, or we can keep it in a cache and produce a new binary. Let's see how to implement this optimization in this example written in JavaScript that finds the element within vector v that is the closest to a given query queue. The size of the vector is passed as an argument. This size is called n. Notice that this is an artificial example. However, its goal is just to demonstrate the optimization. Here you can see the CFG of this program. Notice that it contains two entry points. That's common in CFGs produced by JIT compilers. Can you imagine why there are two entry points? One of the entry points is the typical beginning of a function. The other is an entry point produced to move onto the CFG from interpretation mode. Imagine that you are interpreting the program while you produce the CFG. Then you want to branch into the binary code from where you were while interpreting the program. That's the reason for the second entry point. If we want to do value specialization, we need to know the value of the arguments of the function. But that's easy. We can check the stack of the interpreter while we are generating code for the function. Then we can replace the symbolic names of the argument with their actual values. Another optimization that is immediate is to eliminate one of the entry points. Remember, we are speculating that this function will be called only once. Therefore, we don't need to produce its second entry point, because it will never be used. This observation let us eliminate a lot of code from the CFG. Other thing, we can do also something called array bound checks elimination. These guards, the array bound checks, are there to prevent us from reading memory regions that have not been allocated. But we know the size of the array and we know the limits of the loop because we are interpreting the program. Then we can find use some simple analysis to avoid having to insert these checks. Notice that this analysis is mostly pattern matching. We are looking for the ranges of induction variables in natural loops. We can also run loop inversion in the program. Do you remember this optimization, loop inversion? Essentially, it replaces a while loop with a do while. That has many nice effects. Might eliminate a branch and give us a place to hoist invariant code. Something cool is that we don't need to insert the if then else to guard the loop against no iteration. We know already the limits of the loop because we know the values that are being manipulated by the interpreter. Anyways, there are many optimizations that we can do, but none of them are so effective as constant propagation combined with dead code elimination. Remember that we have made the function arguments into constants. That's like solving lots of computations at compilation time. In the end, we obtain a much lighter version of the original function. Because we have less code to generate, specialization might even reduce compilation time. For instance, there will be much less code to trouble the register allocator. And depending on the programming language, there are other optimizations that we can do too. For instance, in JavaScript we have closures. So we can pass functions as parameters to other functions. But then we know which functions we are passing over. In this case, we can inline these functions. Like in this figure, we could inline the inc function that is used as an argument of the map function. Then, instead of having to invoke the closure within the body of map, we can inline it there, avoiding the cost of a function call and giving the compiler the chance to run some context-sensitive optimizations too. In the end, value specialization let us transform code like this one on the top in a much shorter version, like the program on the bottom of the figure, which we get after inlining the body of inc in map and doing loop unrolling. And with this last example, we close this class on value specialization. In the next class, we shall talk about a kind of JIT compilation called trace compilation. Thank you.